And the other method, the third method I want to introduce in this, also incorporated into this standard, is this load modeling based method. So thinking this way, the nature of CVR is that a load are sensitive to voltage, right? If load are insensitive to voltage, let's say you have a extreme case, all the load are PQ load, constant power load. When you reduce the voltage, what would happen is that your current will increase and your line losses, transformer losses all increase. You will end up with a negative CVR effect, right? You didn't reduce the load, but you increase the loss. You will have the negative CVR effect. And on the other hand, the other extreme case is that you have all the load are resistive load. And in this case, you will have the maximum CVR factor according to Ohm's law, right? But in practice, you won't have either case. What you will have is more like a combination of constant power, constant impedance, and constant current load. We call it ZIP load. And the composition of each part, constant power, constant impedance, and constant power part, each part is changing with time depending on customer behaviors. So if we could somehow identify their compositions, we could use that to calculate CVR factor. So that's the basic idea of this load modeling based method. It's not like so obvious as the previous two methods. You just reconstruct that load profile without voltage reduction. And then you do you see the difference. So that's very straightforward. So this one is a little bit you need to dive deeper, a little bit deeper to understand it. And like I mentioned before, you model the load, the IP load, basically as a combination of this is constant impedance part, this is constant current part, this is constant power part. And this alpha, beta, gamma represents their composition. And if you sum them together, they should equal to 1, right? So what you will need to do is that from the SCADA measurements at the feeder head, you try to identify alpha, beta, gamma. So that's the problem. So it's more like a load model identification problem. So you formulate this problem as an optimization problem. Okay, so you try to minimize, you try to find the combination of alpha, beta, gamma, so that your model output is very similar to your measurements, right? This is P is your measurements, and V is the measurements, and alpha, beta, gamma are something you want to identify. So you will try to select different combinations of alpha, beta, gamma to minimize the error, the difference between your model output and your measurements. So that's a statement, problem statement. So when we do this, we know that we need at least we know that we need to do some kind of derivation. So this is it's actually convex respect to the coefficient. So you can just if you do not consider the constraint, you just lighting the first order gradient to be 0, and then you will find the coefficient. But you do need the 3 measurements, at least 3 measurements to make this happen. So that's why I create a sliding window. Okay, if it's less than 3, you won't be able to do the inverse. But sometimes this sliding window, the size should be at bottom minimum should be 3, but it could be larger. The reason is that depending on if you have consecutive measurements that are very similar to each other, so you need to expand the window size to larger size. So I would say a minimum 3 points to make this equation work. Okay, after you calculate that alpha, beta, gamma using the method I just mentioned, you substitute into this equation. Look at this equation. You have alpha, beta, gamma, which coming from your load identification, and delta V is something you can easily estimate. And then you substitute into this equation, you will have the CVR factor. So that's how we calculate CVR factor. But again, this CVR factor, you can see this little index I representing the time. That means you're doing real-time identification, and then you get the real-time CVR factor, which is not that useful to utilities. The next thing is that you need to use the real-time CVR factor you have identified to reconstruct what would happen if there's no voltage reduction, and to get this P of estimate. And then you do some integration, you will finally end up with a single CVR factor, like I mentioned here. So this is how we do that. Basically, I don't have too much time to go to the details, but the idea is simple. It's just you try to identify the alpha, beta, gamma, which represent the load compositions of constant power, constant impedance, and constant current part, and using that to get the CVR factor. Okay.